So thank you everybody for coming. My name is Leo Durack, and I'm a principal engineer in the AWS Deep Learning Group. And today I'm going to be talking to you about using MXNet, our deep learning framework of choice, for building recommendations models at scale. In this session, I hope to offer something to everybody here, even if you've just barely heard of machine learning and don't really know how it works, or if you've been building deep learning models for a while and know a whole lot about neural networks. I hope that there's going to be something that everybody learns along the way. And the converse of that is that there's some parts that not everybody's going to appreciate. But if we get to the end and you haven't learned anything, come talk to me, because I'd love to get your take on everything that I'm talking about here. But we're going to start out talking about machine learning systems and recommender systems in general, show you how to implement those using MXNet on the P2 instances, using the deep learning AMI, and then go through 3 or 4 different kinds of recommender systems and show you how to build each of them using MXNet. And along the way, we're going to pick up some tricks for handling sparse data sets in MXNet. And we'll tell you more about what that means if you're not familiar with the term. So to start with, recommender systems and machine learning. So recommender systems kind of got their popular start with the Netflix prize in 2006. So Netflix is a great customer of AWS, and in 2006, they released a data set of movies that people had watched and what customers had rated them. And they offered a prize of $1 million to anybody who could outperform the recommender system that they had in-house by more than 10%. And it took 3 years for anybody to claim that prize. And they offered some smaller prizes along the way, but this really set the stage for a lot of the research that happened in scientific communities on recommender systems. And so recommending movies is kind of a staple. And so how you framed that problem is, there are a number of ways to do it, but the way the Netflix prize described it is pretty typical, which is to predict what star rating a user will give to a particular movie. And so to put that in code, you can imagine a function which returns a floating point number on the range of 1 to 5 for the number of stars, that takes in a user and a movie object and somehow makes a prediction. The question is, how do you make that prediction? What do you do with this user object and this movie object to come up with that number? And well, the answer is machine learning. So you use machine learning to come up with this model, and then you run the model, and you feed it in the user and the movie object, and it gives you this floating point number. OK, so what's that process like? So very roughly, you start with some training data, which are examples of the correct answer. What you want the system to do, given a set of users and movies? What number do you want it to give out? And you run that through a set of complex math that's really compute intensive to get the training. That process is called training. Then you get the model. And once you have the model, you put that into production, and you feed in the input data, and what comes out are predictions. So these predictions come out, you get a number, and it's very natural to ask the question, how good is your model? Like, is this number meaningful? Is this useful? And so understanding how you measure that is critical to any machine learning system. And what is typically done is you take all of your labeled data, and labels are the correct answers that you're trying to predict with the system. And you divide it into a part, and you use most of it as your training data, but you leave a chunk of it off to the side. And you put that training data through the training system, and you come up with this trial model. And once you have the trial model, you take the remaining data that you'd set aside, and we call that your test data, your validation data. It means the same thing. Well, subtle difference, but we'll treat them the same here. And you put that test data through your trial model, and you get an evaluation result. And now something really interesting happens at this point, because on that test data, so the trial model has never seen this data, right? You held it back, and you need to make sure that it has no access to it, so you can't cheat. And your model, when you feed the test data in, you don't give it the right answer. You don't give it what customers actually did for those user-movie pairs, but we know the right answer because it's labeled, right? It's from that original data set we have the right answers. And so we can compare what the result is that comes out of the model with what the correct answer was in the original data set, and that gives us our accuracy. And this is the fundamental concept for supervised machine learning, is you you train a model which attempts to generalize from the examples it's seen in order to predict well on examples that it hasn't seen. And the discrepancy between the predicted answer and the correct answer in the original data is your accuracy level. And we'll be doing a bunch of graphs and talking about that accuracy and the error, which is the kind of the opposite of accuracy, how many mistakes it makes. Now, movie data and recommendations data are often sparse. And what do I mean by that? So you think about the data set that is in that Netflix Prize data set. And you can think of it as a giant matrix where, I don't know if you can read that. It's a little small on the screen, I apologize. But every column there on the left side is the name of a movie. Sorry, every row is the name of a movie, and then the columns correspond to users. And in the places where a given user has rated a particular movie, there's a number showing up, a number from 1 to 5. And you see that most of those are blank. And this is why we call it sparse, is because this data set is sparse. It's mostly missing, and we just have a few examples of the correct answers that we're trying to get out of our model. And so let's think about what a typical size of such a data set is. So for a variety of reasons, we're going to use the MovieLens data set, or the MovieLens 20 million data set, instead of the Netflix data set, because it's a lot easier to work with. And we're going to use the 20 million example version of this data set. And in this data set, there's 27,000 movies, and they were rated by 138,000 users. So you multiply that out, that's 3.7 billion possible ratings. But of those 3.7 billion possible entries in that giant spreadsheet or giant matrix, only 20 million of them are filled in. So more than 99% of the possible numbers in this giant matrix are missing, they're blank. And that's what we're asking the machine learning model to predict, is what are the values of those numbers that we've never seen before. Now let's think about what it would take computationally, like put on our computer science hat, and think about storing this matrix. There's a couple different ways that you might do it. You might just say, you know what, it's a matrix. I know how to do that. It's a doubly dimensioned array. I'm going to allocate a single byte for each entry, and I'm going to put a 0 where there's something missing, and a 1, 2, 3, 4, 5 integer where there is something, and it's going to be almost 4 gigabytes. And you know, we could deal with that. That's big, but it's not totally unreasonable. But you can store that much more efficiently if you just recognize that most of those entries are missing. And instead of storing every value, you just store the positions of the non-zero entries. And then I have a proposal for a way to do it. You use 4-bit integers for the IDs of each position, and then you still store a number for each rating. And in this particular case, the sparse representation is 20 times smaller than the dense representation. And that's a pretty big difference. And 4 gigabytes is maybe not so big that you're thinking, I could deal with 4 gigabytes, right? But if your catalog is huge, if you have millions of entries, if you have millions of users using your system, you can easily see that the dense representation can get completely intractable. And moving all those zeros around, it might seem simple, but it really pushes your computational system. And deep learning systems, and in particular, and generally any machine learning system, your computational capacity is going to be stressed out. So sparse representations of data are important. And we're going to bookmark that for a little bit and jump back to the science. So there's a bunch of complexity in dealing with sparse data, but it's important because if you have a long tail of content or of users, then you really need to do this in order to keep your problem tractable. Okay, so how do you solve this problem? How do you make those predictions? You want to fill in those missing entries and try and predict what star rating a customer is going to give. And the classic technique that's very heavily studied and very well understood is called matrix factorization. And this is math. If you took linear algebra, you'll remember that if you have a big matrix like this, you can approximate that as the product of two smaller matrices, one tall, skinny matrix and one short, wide matrix. And there's standard algorithms for doing this approximation. But you can store those tall, skinny matrices and those short, wide matrices, again, in a much smaller amount of space than the very large matrix. And the interesting thing is, if you do that approximation correctly, then the smaller matrices have actually summarized the important information that's in the big matrix. And they've summarized it in a way that makes it tractable and really easy to work with for future analysis. So if you have maybe 100,000 by 100,000 matrix to start with, then for each of those items, if we pick D to be like 64 is a pretty typical number for the reduced dimensionality, then you have a 64-dimensional vector for each item, for each movie in your data set. And you also have a 64-dimensional vector for each user who's using your system. And these are, in the deep learning parlance, often called embeddings. And you can look at them. You can go into that. You can do this calculation, and you can pull one out. And you can see, OK, what's the embedding for a movie like The Karate Kid? And you say, oh, well, it's a bunch of numbers. All right, they're floating points. What do they mean? I don't know. I mean, I tend to think of these embeddings as kind of like hash codes. Right? They're something that the machine understands and the machine makes use of, and you can look at them and you can see them, but they're not particularly intuitive. There's not a lot you can get out of them directly. But what you can do with them is you can compare them. So take Karate Kid and a similar movie from that genre, like maybe Ferris Bueller's Day Off, right? Good classic 80s movies. And you can look at both the numbers, and you can see that in each dimension, they're not too far apart from each other. And you can pretty quickly, without a lot of computation, you can subtract those two from each other, and you can get a distance. And you can get a single number now that tells you how similar any pair of movies is. And as you can see, for just 64 floats, this is super quick. And now you can start to see how these embeddings are a useful tool for understanding this really complex data set we started with. We started with this matrix of 4 billion entries, and now we've reduced it meaningfully to a way that you can compare any set of movies and see how similar they are. So for example, if you were to look at Karate Kid versus a different movie like My Little Pony, you'll see that they're much farther apart. Whereas one, the distance is only 0.1, the other case distance is 1.5. And you can actually do the same thing with users in this model. The users in the movies are embedded into the same space. That's where the term embeddings comes from. So you can measure the distance between a user and any of the movies they might be interested in. And that's the basic idea behind a matrix factorization model. So we're going to run this matrix factorization technique using MXNet. And if you've been listening to our AI story this week, you've probably heard of MXNet already, but I'll give you a little background. It's an open source project. It's been around for a while. It's a year and a half or so. It's been up on GitHub. It's quite popular. Amazon didn't invent it, but we are adopting it as our deep learning framework of choice. There's lots of great deep learning frameworks out there, but we love MXNet for a bunch of reasons. It runs in lots of languages. It's super fast. You can run it on high-end GPUs, on clusters of GPUs. It scales really well to lots of machines. You can run it on mobile devices too. GPUs are important for deep learning models because the math necessary to take that giant data set and compress it down to the summarization that extracts the patterns is really computationally intensive. So we're going to run today on a P2 X-large instance. And that instance, the K80 GPU in there, is capable of over 4 trillion floating point operations per second, which is kind of incredible. It has 2,000 CUDA compute cores. I think it's 2,000 compute cores running in parallel. So you've got your 4-core machine, you've got your 32 large instance. One of those GPUs has thousands of instances in it, or thousands of cores in it, and that's how it's capable of achieving this ridiculously high throughput on floating point math. But it's not a general purpose thing. You're not going to run a database on it. But they're excellent at math, at vector math, and particularly these large matrix computations, which are the bread and butter of deep learning systems. And when you're programming a GPU, one of the problems is actually keeping those thousands of cores busy. And GPU programmers refer to this problem as feeding the beast. There's thousands of cores that want to work on a problem, and so you have to get the data to those cores very quickly. And in order to do that, the GPUs have their own dedicated RAM. And there's an incredibly fast bus between the GPU's RAM and the GPU cores. And that bus is much faster than the PCI bus, which connects it to the CPU, or the Ethernet, which is going to connect it to other machines. And this is for a P2XL. For the P2 16X large, we actually have 16 of those GPUs connected over that kind of medium speed PCI Express bus. I point out all of this because there's a lot of complexity in getting those incredibly powerful instances to run efficiently. They are very, very powerful, but getting them, feeding the beast and getting the data to those machines and scheduling all of this work is very complex. And this is something that MXNet excels at. And so here's a chart on a benchmark image analysis problem where we're training a deep neural network using MXNet on, for the first several bars, a single machine, and then going to 2, 4, and 8 machines. And you can see that the orange line, which is how fast MXNet is performing, stays very, very close to the theoretical ideal speedup, which is what you would expect to see on something that's scaling very well. So let's jump back to matrix factorization and try and visualize what matrix factorization would look like as a neural network. So neural networks start with the input at the bottom, and in our case, we have the item or the movie on the left and the user on the right. And the first thing we do is embed them into this low-dimensional space, and that embedding is that tall, skinny, or short, wide matrix that we showed. And then we compare the two of them by taking the vector dot product, and then we try to predict the rating as a number from 1 to 5. So the system's going to spit out a number, and then we're going to compare that to the correct answer, which is what the user actually rated that movie as. And we're going to run this using the deep learning AMI that AWS maintains. It has a bunch of deep learning frameworks installed on it. We're going to use MXNet. And I'll say the AMI, we published it. Maybe it was a little early, but when we first released it, it didn't have all of this stuff pre-installed. It didn't have the CUDA drivers and cuDNN. And so if you go to the web page for the deep learning AMI, you'll see some of the early people who tried it out. They left some bad reviews, which we deserved. And we addressed those concerns. So I invite all of you to click past those initial bad reviews and try it for yourself. And if you like it, consider leaving a nice review for us, because we really have addressed, I think, every one of the concerns that those initial reviews left for us. And it comes with Jupyter and a bunch of Python libraries. And without further ado, let's go ahead and try and run it. All right, what's going on? Is it working? There we go. OK, so this is a Jupyter notebook. And Jupyter is an interactive Python shell. So it runs in your browser, and it's connected to a Python kernel running on the P2 instance. And where's my mouse? There we go. And you can see the code, and it's a REPL loop. So it reads, evaluates, and prints. And that's a loop. And the code starts out just importing a bunch of libraries. MXNet and those other ones are the sample code for training the matrix factorization algorithm. And all this is up on GitHub, and I've got the link at the end of the presentation. And the next thing we do is we load the data set up, and we count how many users. So we're just going to use the 100,000 sample version of the data set now so that we can actually run through this in a live demonstration rather than the bigger versions. And there's 1,000 users and not quite 2,000 movies. And we're going to define this matrix factorization model. And the lines of code that you see right here are replicating that diagram I showed you. And in fact, at the end, that last line of plot network is going to show this is the machine-generated representation of the compute graph. So the computation starts at the bottom. There's the user and the item inputs. We run the embeddings. We multiply. We sum it up. We flatten it. And then we compare it to the score with a linear regression loss function. And that loss function calculates the errors, and it reports the RMSE, the root mean squared error, which is a measure of how badly the system did. So we want that number to be as small as possible. And let's go ahead and run the thing. And so now we're firing off those thousands of compute cores, and you can see the, you get this? Yeah. You can see the network training as we go, and it's plotting this learning curve along the way. There we go. That's about right. And so you can see that over time, as the network ran, it started out with an error, RMSE error of over 3.5. So on a scale of 1 to 5, if your average error is about 3.5, you're doing horribly. But it very quickly started to converge toward a good answer. And then at the end, you can see it was, it got down to about 1, right? So that's not bad on a scale of 1 to 5. And so let me talk about these two lines here, right? So there's that thick green line, and then there's the lighter blue line. So the lighter blue line is the errors on the training data. And the green line is the errors on the test data or the validation data. And as expected, the system does better on the training data where it's seen the right answers. And on the data where it's never seen them before, it's not doing quite as well. But they're actually pretty close to each other, and that's encouraging. This is a sign of a machine learning system that's actually working pretty well. And I encourage any of you, as you're working in machine learning, to plot these learning curves, is what these charts are called, and pay close attention to them. Because if you see something that looks roughly like this, then that's actually a really good sign. That means your system is behaving well. Your error starts out high, it goes down, and it flattens out. This is actually a really good sign that your system is behaving correctly and doing about what you want. If for some reason you saw that the error on the test data was lower than the training data, you'd be pretty suspicious that you probably have a bug in your code if you see that. So okay, so there is a basic matrix factorization system. And I wouldn't call that deep learning, except for the fact that, I mean, I really wouldn't. It's running on GPUs, and so you're running into a lot of the complexity of building a deep learning system. But a great thing about running this stuff in MXNet is that with just a couple extra lines of code, we can add in a set of nonlinearity by adding a ReLU layer and then another fully connected layer. And we do that, and now we actually have a neural network. So visually, we've just added a couple more compute nodes to the compute graph. And now, when we run it, you'll see that, again, the error starts out high. And I don't know if you can read this. There's a 3, 2, 1. And it converges much faster. It gets down to about 1 much more quickly. And you can see we actually got below 1 on this one. So this one's doing better, right? And that's not a surprise. Generally, when you add nonlinearity to a machine learning system, you are increasing the expressive power of your machine learning system. It's able to find more complex patterns in the original data. The trade-off is that these systems are harder to train and they're more finicky. But with a nice, powerful framework like MXNet, you can paper over a lot of those differences. So we saw that one did better. Let's compare the results. Let's put them side by side on top of each other, and we can see that it becomes very clear that the nonlinear model got to a better answer, a lower error. So down is better here, right? But you might be saying, hey, it took longer, right? This x-axis is time. That's actually like wall clock time, which is what matters. Even though they both had the same number of epochs, they both had 15 passes through the data, but the computation was more intense for the neural network, and so it took longer. So you say, hey, that yellow line is still going down. What if we let it keep going, right? It's perfectly fair. Let's let it keep going, right? And if we do that, well, gotta restart. But it's gonna drop down again, and you're gonna see that eventually. Whoa, I'm messing this up. Get back there. There we go. And is it gonna get down below 1? How low did we get before? We got to 0.95 or so, right? And here. This one I got below 1, and it's still going. And I'll tell you, it does keep going down, but the thing is, the optimizer that I'm using in this case, the standard SGD optimizer, which pretty much everybody supports, is not the fastest computational way to optimize all of those parameters. And a good neural network framework will give you access to a better set of tools than that. Is it done? Yeah, it finished. So let's plot them against each other again and see how they do. And you see, yeah, given long enough, maybe it's going to get there. But I want to speed this whole process up. Let's switch to another notebook over here where we're using a fancier optimizing algorithm called Atom that's built in. And in MXNet, all we have to do, all this top code's the same, produce the same model. And all I do is I just add this flag saying I want to use the Atom optimizer, which is this adaptive rate optimizer, and let it run. And it's going to get to the bottom much faster. So this first one, again, is that linear matrix factorization model. And you see it quickly gets down to 1 and even gets below 1. And then you're going to see something really interesting start to happen, which is, you see what's happening now? That green line is flattened out, and it's starting to go up. Right? And that blue line is going down, down, down. Interesting, right? Now, again, this is actually totally healthy and normal for a machine learning system. And this phenomenon is known as overfitting. And what you're seeing is that the system is making really, really good predictions on the blue data, which is the training data where it's seeing the right answers over and over again. And it's getting so good at that that it's not generalizing as well, that the predictions it's making are getting worse for the test data that it's never seen before. And this phenomenon of overfitting is really one of the really fundamental issues in any machine learning problem, is how do you control this? How do you learn a model that learns patterns that don't just apply to the data it's seen, but that generalize to data that it hasn't seen? In fact, I'm sure all of you could come up with a machine learning model that gives perfect answers on the training data. You just use a hash table, right? You just say, have I seen this before? If so, what was the answer? OK, I'll spit that out again. Trivial, right? You get 0 error on all of your training data, but it doesn't generalize at all. It's totally not useful for making predictions on unseen data. So controlling this overfitting problem is one of the great issues in any machine learning system. So let's try running, again, the same thing using the Atom optimizer for the on the nonlinear neural network. And while that runs, I'm going to show you an even fancier neural network. So another great thing about using a framework like MXNet, even for a simple problem like matrix factorization, is that you can easily pull in all these ideas from elsewhere. So I'm going to borrow some ideas from ResNet, which was the neural network design that won the very competitive ImageNet competition this last year. And I'll show you what this neural network looks like as soon as this thing's done training. And it's going to, this is going to be a very deep neural network with a whole lot of layers and skip connections. Here it is. And you can see that we start all the way down here. We look up the embedding, and then we apply some nonlinearity. We use this technique called dropout, which is a really aggressive regularizer. Regularization is the key way to avoid this overfitting problem, or it's really one of the fundamental building blocks for doing that. And so you can see there's this fairly complex computational graph with these skip connections, which allow it to compute the residuals, which is the source and name, the ResNet. And now, when we run this one, I use a slightly larger batch size so the GPUs can run more efficiently, and we can actually see this thing go in the course of a demo. And it quickly gets below 1 again. And we'll actually see that with the dropout regularization, even though the model is very complex, it's not going to overfit. In fact, it's going to slowly go down, 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 and we'll get to an ultimate answer of about 0.92 or so, which is significantly better than any of the other models get. And this is a pattern with dropout, and that it can take a very long time to train and get your answer, but it often gives you very good results if you're willing to wait that long. And these are kind of the happy trade-offs, right? Do I want to wait longer and get better results, or not? I mean, sometimes you can wait longer and get worse results, but there's a lot of playing around that you can do with this stuff. So while this thing is running, I'm going to jump back to my slides. Where are they? There we go. Go back. OK, so all of that was framing the problem as predicting what star rating a user would give to a movie. And that's a fine way to frame the problem, but sometimes it makes more sense to frame the problem as a binary prediction problem, which is to say just, would the user be interested in this movie or not? Yes or no, not a 1 to 5. And the reason for that is that, well, consider a movie like Xanadu with Olivia Newton-John and Gene Kelly. And if you go and look at the ratings people give this movie on IMDb, they are not good. But sometimes you just want to watch Olivia Newton-John rolling around on roller skates, right? Even though people are probably going to give it 1 or 2 stars, maybe that's what you're in the mood for. And on the flip side of that, take this movie, which I think is called Andrei Rublev. Apologies for anybody who actually speaks Russian. Pretty much everybody who watches this movie gives it a 4 or 5 stars. But not that many people watch this movie, right? So if your goal is to try to predict what star rating somebody is going to give, then Andrei Rublev is going to get recommended to a whole bunch of people who have no interest in watching a movie about a Russian writer in the 60s. Right? So reframing this problem as a binary prediction problem can often give you better results. So instead of having a 1 through 5 number, we just replace all of those numbers with 1. And in fact, this makes the problem significantly easier in a bunch of ways too. And so consider like this subset of the data where I like my 80s classics, and those each get a label of 1, and my daughter likes her cartoons, and they each get a label of 1. And now think about building a machine learning model that's going to predict this. So now you're saying, OK, predict the score for a given user for a given movie. And you know what? That's pretty trivial to write. Everything's 1, right? And in fact, if you fed that same data into the machine learning system, it would very quickly figure out that this is the best model as well. But that's not useful, right? That's not what we want. So the way around this is a technique called negative sampling. So what you do is you shuffle the data around so that we infer zeros in places where there were blanks on that matrix before. And the efficient way to do this, it's definitely not the theoretically best way to do it, is to just take the data in the chunks that we read them off the file, and we shuffle each of those chunks. And we replace the 1 with a 0 everywhere we shuffled it. And MXNet has a tool for doing this called the negative sampling data iterator. And so any data iterator that you define, and that's how you read your data off of the disk, the negative sampling data iterator will shuffle around the many batches and replace them with a fraction of, or actually a multiple of examples of negative case. In this case, you usually want more negative examples than positive for, I don't actually exactly know why, but in practice that always seems to help. And so a ratio of 3 or 5 or something like that, sometimes people go as high as 20, seems to work well. And so this negative sampling data iterator helps with that. And we can see that run in another notebook here. Which way do I go? I go over here. There we go. And so the code, again, looks very similar. We load up the data just as we did before. And now we use the decorator pattern. We just wrap it. We take the positive training data, and we wrap it in this negative sampling data iterator, and we say we want the sample ratio to be 3. Then we define basically the same neural network. I'm using a cosine loss layer instead of the logistic regression loss that we had before. And I'm using it, which inserts these L2 normalization layers in the way. And then we run it, and now the scale has changed. So instead of being on a scale of 1 to 5, now everything's 0 or 1. So the error numbers tend to be closer to a half. And you can see again, that was maybe a bit too much, that it's learning along. And we have this nice learning curve, which is about the shape that you expect a learning curve to be. So the errors are slightly higher on the evaluation data that the system's never seen before. And so it's training. So OK, that's how negative sampling works. How am I doing on time? Oh, not too badly. And you could go and, so the neural network structure up here is, again, pretty simple. We don't have any nonlinearity in this place. We don't have any explicit regularization. But you could totally go and apply all of those tricks that we did on the rating prediction case here and try and figure out what's going to work best in order to get that validation error as low as possible. And how's it going to end up? And end up down around 0.46. That's pretty good. OK, so I'm going to get out of here. Yeah?
You seem to have provided some default values, example of sampling to 3 and some of the parameters as well. Have you done some cross-validation earlier? That's how you came up with these parameters?
All right, so let me repeat the question. So there's and I'll rephrase it slightly. There are some seemingly arbitrary choices that I made, like picking the sampling ratio to be 3 and the learning rate and things like that. And the question is, where did I come from? And the person asking the audience clearly knows the art a little bit. Just said, did you cross-validate? And I haven't in this case, but that would be the correct thing to do, because just as you can overfit your training data, if you spend too much time fiddling around with all of these arbitrary choices, you can also start to overfit your testing data. And then you can convince yourself that you have this amazing answer because it reproduces that 25% that you happen to hold out really, really well. But you might just be getting lucky because you spent so much time fiddling around with these numbers and that you picked something that just happens to work very well for that. So if you do spend a lot of time futzing with these numbers are called hyperparameters, then you actually need to hold out a third set of data. You need to divide your data into 3 sets, one for training, one for validation to see how well each individual model is, and then a last one that you never touch until you're done futzing to see how well the system is actually performing. So that's a great question. Let's see if we can get back to this demo. Or get back to the slides. All right. So that's all well and good. If the only thing that you know about your data are the interactions between the users and the movies. But in the real world, we often know a bunch about our users and a bunch about the content that they're interacting with beyond just their unique identifiers. Because everything we've done so far, both the users and the movies are represented just by unique IDs. But in the real world, we know these behavioral interactions, but we also know things like the names of the movies. And so you might think to yourself, the movie name My Little Pony, it's got the word pony in it. And so maybe the person who watches that movie might want to watch other movies that have the word pony in it. Or Ghostbusters and Ghostbusters 2. You don't need a bunch of training data for the system to realize that those two movies are probably related to each other. Similarly, you usually have pictures for whatever it is that you're recommending. And nowadays with deep learning systems, we have really powerful tools for semantically understanding what pictures mean and what they represent. And as far as your users, you probably know a bunch of things about your users, but something that generalizes quite well is the words that they've searched for tend to capture a bunch of things that are meaningful about what their preferences are. So you can imagine, and we'll talk about this, taking each of these things as inputs into a recommender system as a way to improve the quality of the recommendations that come out. And the question is, how do you represent each of these ideas as a neural network? In the neural network. So neural networks, they're fundamentally math, right? So to get to get them to consume anything, it needs to be numbers. It needs to be in a vector form. And if you have a unique identifier, like we've been using for our users or our movies, then an embedding is a great way to do it. So you have this one-hot representation where you just pick a dimension on your embedding matrix, and that is their identifier, and then you learn that vector representation for them. So we know how to do that. For images, something called a ConvNet, which is short for a convolutional neural network, have really become the de facto way of processing images in the last several years because they just dramatically outperform everything else that people have been doing. And again, a nice thing about working in a deep learning package like MXNet is that these things are just ready off the shelf. You just pull in a line of code and pay whatever computational cost you have to. But in terms of coding, it's very simple to pull in a convolutional neural network to process your images. Similarly, for text, the standard way of processing text in a neural network these days that seems to perform best and generally across a variety of tasks is called the LSTM, or long short-term memory, which is a strange term that I won't bother to explain. But this can take an arbitrary sequence of things and understand it and process it. These things are still, they're not reduced to practice in the way that a convolutional neural network is. They're still kind of finicky to work with. And so here, I'm going to suggest an alternate standard representation for text, which is called the bag of words. And here we ignore order, and we just say, take all of the words in whatever it is, your search queries or your movie title, and you throw them in a bag. And you count up how many times each word shows up. And again, you make one of these sparse vectors where everything's 0 except the words that show up, and you put a number there, usually 1, or you can count, actually. And that's a bag of words representation. And it's not as good as the LSTM, or the recurrent neural network representation, but often it's good enough, and it's a heck of a lot easier to work with. And to put these together, we're going to use a neural network design pattern called the deep structured semantic model. And this is really a beautiful design pattern for neural networks. And I think it's really underappreciated out there. Like the ConvNet and the LSTM are things that most people working in deep nets are very familiar with. The DSSM is a brilliant way to combine pretty arbitrary sets of content. You can represent your left object and your right object, and in our case, it's the user and the movie or the item, with pretty much anything you want. And you come up with some way to compress the representation down to an embedding. Then you combine the individual embeddings for the different pieces to have a combined embedding. You measure the similarity, and then you predict the label. And this works across a really wide variety of problem types. And in this case, we're going to use the cosine loss layer that I mentioned very briefly earlier, which it's a dot product, but it ignores the length of the vectors. And so it's just comparing how close they are. If you think of the vectors as pointing in a direction, what is the cosine of the angle between them? And 1 minus to make it look like a loss, so that when they're pointing in the same direction, you get 0. And this is another thing that's available in MXNet for making recommendations systems. I'll give you a very, very kind of brief demo of this. I'm not actually going to train a DSSM because they're complicated, they're rich, I think they're beautiful. But even finding a data set and getting one ready to do this would be a chunk of work. But I'll show you that with really just a few extra lines of code, you can start out with your image. And up here, all I did was I just imported AlexNet, which is probably the most well-known convolutional neural network. It's not the best performing, but it's really well-known and relatively simple. And we passed our image through the AlexNet to get the features. We pass the title through the sparse bag of words projection layer, which is an efficient way to take a very high-dimensional sparse representation and compress it down to a medium-dimensional representation that you can easily work with on a GPU and a neural network. And we do the same thing for the user's queries, and we put them together, and I'll show you what this neural network looks like. Oops, I hope I didn't erase anything there. No, OK. And again, the same pattern at the top. We're trying to predict the label. We have some comparison. and we get the two embeddings together, but then you go down further and you see that those embeddings are themselves a combination of other embeddings which are generated from either the user ID or the search query or the title words in the movie, or this one's the image, and if you follow it all the way down, this series of operations is that MXNet, and at the very bottom is the image itself, which is which goes through that convolutional neural network to semantically understand the content of the image. And so this is a pretty complex neural network. I'm not going to try and train it for you here today, but the idea is that using MXNet, it's really easy to express these highly complex ideas for how to. One of these days, you'd think I'd figure out how to get this thing back again. There we go. For how to combine these things using a DSSM. And I've got a couple of inspirational references, the canonical paper describing DSSMs, the paper on YouTube recommendations that came out recently uses a lot of these ideas, and I love that order embedding paper as a different application of the DSSM. You all want to take some pictures? These slides will be available somewhere. I'll tweet them when they get up. And this is, like I say, this is a great set of techniques if you really want to start pulling in diverse sets of data in order to improve your recommendations. Another trick, if you kind of want to go the other way, away from the highest possible quality, but emphasize scale and computational speed, is to use user-level modeling, user-level models. Now, think about when you've got those embeddings. What are you going to do to make those predictions? You need some function, which is to get the top movies for a user. Well, like I said, you have to compare the distance between your user and each of your movies. And you might think of this as kind of a geometric search problem, but when you get up to 64 dimensions, things like KD trees turn out to just not work. And so what you need to do in practice typically is just go through every single movie and run that comparison to get the score, and then you sort that and you pick the top movies. And this might seem like if you have a big catalog, like it's going to be computationally intensive. And yeah, it can be computationally intensive to do this. So these embeddings-based strategies can be difficult to work with at large scale. So wouldn't it be nice to just get all of those predictions all at once? Train a single model, which takes in the user, and it spits out a set of recommendations for every possible movie that the user is interested in. And then you just sort that and you're done. And conceptually, this might seem like a bit of a cheat because that model might be doing the exact same thing under the cover. It might be going through that tight loop of comparing every movie. And in practice, that's actually true. But remember, again, how these GPUs work. If that model is running once in the GPU using the highly optimized deep learning framework, then that thing can run orders of magnitude faster than any control language. Any Python or JVM code that you're going to write is going to be dramatically slower than something that's actually built into the model. So having a single model that does all of this for you at once can give you really big speed improvements and really big scale improvements. And so what that looks like, well, there's a bunch of ways you might formulate it, but you might formulate it as an input bag of movies, which is analogous to a bag of words, and an output bag of movies. And the question is then, how do you represent what the user has done into an input and output? And typically, people will just put some time-based cutoff. Like maybe you'll say, pick a point in time and say everything before that is the input, and you're trying to predict future movie consumption in the output. Or you'll say, let's try and predict just the very last movie that they watched, or the next 5 movies, or something like that. And you can run a neural network like this. And a key difference here is that now this is a multi-label neural network. So instead of just predicting a single number, now we are predicting thousands of numbers. We're predicting thousands of zeros or ones. And those output values are sparse, just like the input values are sparse. And so you need some special tools to deal with this efficiently. And another thing that comes up is that with these sparse data, you have some number of movies in the input and some number of movies in the output. And conceptually, we're just storing the IDs for each of them. You got a bunch of IDs in the input, a bunch of IDs in the output, and you're going to feed all of these into the neural network. Now, GPUs, like I say, they love crunching on matrices. All right, matrices are rectangles. And if you have a variable number of entries in each row of your matrix, then it's not a rectangle anymore, right? It's got this kind of jagged edge. So what you have to do, well, one way, and a way that I recommend to deal with this, is you just pad it out to the end with something that indicates that it's supposed to be blank. -1 is what we've used in our code. This means that in some cases, you need to pick a cutoff value, and you probably have some tail users that are crazy and they watch hundreds or thousands of movies, and you're not going to be able to represent everything they've done into the size of the matrix, and they're going to get clipped. Okay, whatever. They're the exceptions. And you're going to have some -1s on the end, and this works well. And on the output side, you need a different kind of loss label that can deal with these multiple predictions simultaneously. And a good loss function that we've introduced in this package that I'm sharing with you all is a cross-entropy loss that's good at making thousands of simultaneous predictions on these binary labels. So all of the stuff that I showed you is available for you to try for yourself. So here's a link to the Deep Learning AMI. Again, I encourage you to try it before passing judgment based on the early reviews. We do listen to feedback, so if you do find anything wrong with it, please do leave us a review and we will address that as well. But I really do think that we've gotten it to a pretty darn good shape. In fact, we just added CPU support. MXNet runs very well on CPUs, and with these new C5 instances with the Skylake processors and the AVX512 instructions, you can actually get pretty good floating point performance out of a CPU. And we've got Intel's MKL BLAST library preloaded. And so you don't have to pay for an expensive GPU instance to run this stuff, to try it out. And all of the example code is posted up on GitHub in the MXNet example section under recommenders. And with that, I will thank you.